Next up is for gas liquid solutions. So you're looking at gas liquid solutions first. Next up, we'll start looking at liquid solutions now and solid liquid solutions. So first up, we will now consider liquid solutions and solid liquid solutions. Now, when it comes to solid liquid solution over here, what happens is by this time we have started learning more about liquids and solutions. We are now learning more about each of these here. What have we learned about for a liquid here? We have learned that boiling point for a liquid is going to be inversely proportional to the vapor pressure of the liquid. That is what we have come to understand over here. Let's try to analyze this point a little bit more carefully here. What does boiling point mean? Define boiling point, please.
The temperature at which
Liquid becomes gas.
liquid becomes gas.
So
But evaporation also.
let's try to understand each thing patiently. So what does temperature at which liquid becomes gas truly mean here? Because as you just correctly pointed out, evaporation is a process which happens naturally at all temperatures. Liquid is becoming gas there also. Why is that not boiling point? What does boiling point truly then mean? So let's try to understand boiling
the
point
molecule.
from the point of view of vapor pressure. So what is going to be happening to vapor pressure as you increase temperature?
Decreases.
Stop. Think. What is vapor pressure really? Vapor pressure is going to be the
Increases.
constant.
It increases.
Let's discuss it in every different way possible. It's the equilibrium constant. For what? For liquid in equilibrium with gas.
Increase in temperature favors.
Why does it favor forward?
Because first of all, the gas has more energy, so more collision. So more.
Stop. We have done thermodynamics recently.
Yeah.
Liquid to gas in the forward direction. What is enthalpy change?
Oh, liquid to gas. 1 second.
Liquid is becoming a gas. You have to supply energy or remove energy.
You have to remove energy.
Liquid is becoming a gas.
Sorry, supply energy. My bad.
So this is going to be obviously positive and endothermic.
Positive, yeah.
Is an endothermic reaction?
Yes, yeah.
The enthalpy change is positive.
Yeah.
The equilibrium constant. What will happen to it if I increase temperature?
Okay, so forward, yeah, it favors.
Forward direction is favored, equilibrium constant increases.
Yes, sir, yeah. Endothermic.
That is one way of looking at it and understanding it. There are lots of other ways of looking at the same thing. Let's now try to understand one other way. In this particular case here, this vapor pressure was basically the equilibrium between what and what?
Water liquid, water gas.
Basically, what processes? Evaporation and condensation.
Yes, yeah.
Correct?
Yeah.
If I increase temperature, what is going to be happening? My liquid molecules will have more energy. They can escape more easily into vapor phase.
Exactly, yeah. So evaporation is favored.
Correct. So evaporation is more easily favored. Evaporation will increase by a good margin. Condensation also will increase actually. Why? Because there are more molecules in vapor phase now.
But
each individual molecule is having more energy.
So
for
more
individual molecule, it needs more attraction to basically now go into liquid phase. Because the individual molecules in vapor phase also have more energy now. So even though I have more molecules in vapor phase available, condensation has increased, but the amount it has increased by is lesser than the amount by which evaporation.
Same with endothermic, exothermic.
Correct, exactly. The same principle happens over here. So you end up having condensation increases, but it increases by like say 1x. Whereas evaporation increases by like say 2.5x. So you end up having more molecules present in vapor phase now.
Yeah. Okay.
Which means more pressure on top of the liquid.
Yes, yeah.
So as we increase temperature, What is going to be happening? Vapor pressure.
Temperature increase. Yeah.
Okay. What happens is this. At boiling point, think of boiling point as the temperature at which all of the liquid suddenly wants to go into vapor phase.
Yeah, all the liquid. Yes.
So what is going to be happening over there is very simply this. You're going to be having all of the liquid suddenly achieving an equilibrium with the vapor. So what is happening till now? What has been happening till now is the liquid is producing vapor.
Hmm.
That vapor is being pushed down by the atmosphere from outside.
Yeah.
Correct? And the atmosphere is the one which is actually preventing the liquid from escaping out into atmosphere, out completely into gas. Right? Think. If I have a liquid present as a liquid,
Yeah.
what is forcing the molecules of the liquid to stay attracted to each other? The atmospheric
Yeah.
pressure on top of them.
Yeah.
So if currently the vapor pressure is now pushing against everywhere, it is not just pushing against liquid, it is also pushing against atmosphere also, correct?
Correct.
So at the boiling point, what happens is you're going to be having
Equal atmospheric
pressure
pressure.
becomes equal to atmospheric.
It's okay.
What happens if it becomes equal to atmospheric pressure? It completely pushes it away and it escapes outward completely. Think of it as I'm going to be having, imagine a container. All right, I'm having a normal container. Imagine a container where there is some liquid present. This liquid is going to produce, what to say, particles in vapor phase.
Yeah.
Which are going to be stuck around like this. Of course, they will also be blown out by the wind also here and there. But what is overall effectively happening is atmosphere is continuously pressing on top of it. Right?
Yes.
So the atmosphere is constantly pressing down on top of it. At this point here, the liquid molecules in vapor phase now gain enough energy to push back against the atmosphere completely and still escape of it.
So all the gas
All
molecules.
of them will keep getting out because now the equilibrium is now pushing continuously in the favor of gas molecules escaping.
Only thing stopping it is the atmosphere.
So originally what was keeping them tied down was the atmosphere.
Okay.
Like a blanket on top of them.
So then what about if there was a vacuum?
Think.
Then
Think. Exactly what you're thinking will happen.
it's
In vacuum, there is no vapor pressure applicable. There is no atmosphere, correct?
yeah.
There will be no liquid.
No liquid.
Yes, there will be no liquid. All of the liquid will evaporate off.
Oh.
Why?
Temperature is
No, vacuum, na, you keep removing the gas. Na. What are you doing? You're doing the same principle.
Oh yeah.
Why did the liquid vaporize off completely at this temperature? Because as the vapor particles are getting more comfortable at pushing against the atmosphere and leaving, they leave. As they leave, this evaporation keeps happening more and more. Because there is no way condensation can happen now.
Yeah.
Why? Because molecules are escaping
Forward reaction.
against the atmosphere.
Yeah.
Leaving. समझ में आ रहा है कि क्या बोल रहा हूं मैं? That is the idea here is you're going to be having at the boiling point, all the liquid molecules are comfortably, easily going to become vapor, mainly because the moment they become vapor, they now have enough energy to push against the atmosphere and escape out.
Some more freedom, basically. Yeah.
Yes. So they're not going to be getting trapped on the surface over there or on top of the container there. They will just fly away. They just escape out.
So then sometimes all of the water does not boil, right? I mean, does not evaporate.
Slowly, obviously. You think
So,
it happens slowly. And
slowly, yes.
what happens eventually? When will all of the water not boil? It's called a sauna. Right?
Yeah.
What happens in a steamer or in a sauna?
It's like a closed area, right?
Yes, correct. So basically, you're having the enclosed region. That's why you start sweating a lot more.
It's like
Because a lot of
equilibrium.
water vapor present in the atmosphere.
Yeah.
Right? Same thing happens. Same thing happens here. Why does it not boil away? Well, very simply because of that. The entire atmosphere is extremely rich in water vapor then. That's why it probably doesn't boil.
Okay, okay, okay. Okay, got it. Yeah.
It had some ventilation, automatically it will boil off.
Correct. Yeah.
You understand
Yes.
the idea there?
Yes, sir.
If
Yeah.
it is vacuum, what will happen there? Liquid evaporates off fully. Because you're removing all the vapor.
Hmm.
There will be no liquid.
Yeah. Yes, sir.
That's basically what happens in a vacuum. Now, where did we suddenly, why did we suddenly, yes, so boiling point is going to be the temperature at which we are going to be having. So if I have to talk about what is boiling point here, it is going to be the temperature at which vapor pressure becomes equal to atmospheric pressure.
Hmm.
So this is basically what is going to be your boiling point for a liquid over here. So this is going to be the next aspect here. So now we will start looking at other solutions. First up, we're going to be considering, what to say, next thing, let me quickly introduce the next characteristic here by discussing one type of solution here. So we will first start off with a solution of non-volatile solid in volatile liquid. So basically non-volatile solid now, let's say sugar and water.
Hmm.
It's a non-volatile solid with a liquid water here. So what happens in this particular case here is very simply like this. So if I'm going to be taking a solution, let's say I'm going to be taking a solution which contains, say, in this case here, I'm going to use different colors. I'm going to call water the liquid as A, and I'm going to be calling sugar the other particles as B. I'm going to represent them with different colors. So water is going to be particles A. So most of the surface is going to be containing particles of A, but a little bit of it will contain some particles of B also. How much of it will contain what? Well, that is dependent on the concentration. Why? Because it's a homogeneous solution, correct? A proper true solution. So this guy became a true solution. This means this is homogeneous.
Hmm.
This means evenly mixed. All right. So if it's going to be an even mixture here, now let's try to understand how evaporation is actually going to be happening and how vapor pressure is actually going to be really created. So let's say I'm putting a lid on top of this. So the lid is put over here. What happens is you're going to be having water molecules getting collected.
Hmm.
Now, the only problem here is this. The water molecules which are getting collected here are lesser in number, mainly because evaporation, which was very much necessary for creation of water molecules in the vapor phase, is dependent on the surface because the surface phenomenon. It happens based on the amount of surface it is occupying. And vapor pressure is also a surface phenomenon. Right? Vapor pressure is also a surface phenomenon.
Hmm.
Why is vapor pressure a surface property? Because vapor pressure applies on entire surface of the liquid solution, full surface. Whereas evaporation can only happen from the part where the liquid is present. Wherever the non-volatile solute is present, no evaporation can happen.
Correct.
Wherever the
Yes.
sugar particles are present, these guys are present, no evaporation happens over there.
Hmm.
Because they are sugar particles, they are non-volatile solutes.
Hmm.
Whereas
Yeah.
wherever the water molecules are present, evaporation can happen. So evaporation is going to be
Dependent on concentration.
correct. So
Yeah.
evaporation, which is going to be in turn deciding partial pressure of gas, or you can say partial pressure of gas above solution. In this case, what gas am I talking about here? I'm talking about water only.
Water, yes.
The partial pressure of water above solution. Evaporation is going to be deciding that. And that guy depends on surface occupied by water.
Hmm.
Correct?
Okay, yeah.
Right?
Yes, sir. Yeah.
Which is going to be in turn dependent on mole fraction of water molecules.
Okay. Hmm.
Because you're going to be having this depends on surface occupied by water now. It depends on basically what then it depends on what is the fraction of water present on surface.
Correct.
How much
Yes.
water is there?
Yeah.
It's homogeneous mixture.
Yeah.
That means the fraction of water present on the surface is the same as the fraction of water present everywhere else.
Yeah.
Right?
Hmm.
Fraction on surface is going to be same as the fraction everywhere else. Which is this. Right?
Hmm.
But my vapor pressure is going to be on the entire surface.
Hmm. Okay.
So my evaporation actually decreases now. But my condensation does not change much. So you'll have a little bit reduced vapor pressure here in this particular case here when you're having a non-volatile solute in a particular mixture present over here.
So once again, why is vapor pressure a surface property?
Think it is pressure exerted on the entire surface.
Ah, yeah.
The pressure, pressure is a surface property, right?
My bad. Yeah, correct. Okay.
That's what. Nothing else over there. So you're going to be
So,
having this particular case.
hmm. Why are you specifically writing above solution?
Where
Is it like pH, partial pressure of H2O? Sorry, vapor
I'm just writing
pressure.
it because I have to make sure that you understand what is the context over here. It
Okay,
is
I understand.
above the solution in the sense we are discussing the solution specifically here. So for this
Ah,
solution, we are talking about it.
okay, got it. Yeah.
So it is in comparison with what? So if I'm going to be putting this out now in a more meaningful manner, let me put it up now here. So partial pressure of water as a vapor above the solution at given temperature T. This is going to be lesser than what was expected for it if it was a pure solid.
Oh, yes, correct.
Okay, so this will be lesser than partial pressure of water as vapor above pure water
Hmm. Yeah.
at temperature T. What is this actually? This is of course going to be nothing but vapor pressure
Vapor pressure. Yeah. Idea.
or Kp.
KP. Yes.
This is also written by another terminology, pH2O naught.
Oh. Hmm.
Yeah. So when you see pH2O, this particular fellow is generally written simply as pH2O
Hmm.
or P
Yep.
liquid. Whereas that is going to be given the terminology with a not over there.
No.
Now, the next thing to basically look at over here is this is going to be something for this particular solution is lesser,
Hmm.
right? So what happens next is you're going to be now having one very interesting property here, which is called as lowering of vapor pressure. What is this lowering of vapor pressure? This lowering here of vapor pressure can be written as the difference in the vapor pressure. between these two. You understand the idea here? So if it is
Yeah.
difference in vapor pressure between these two here, how will that be working out here? That will very simply work out as P naught of H2O minus P of H2O,
Yes.
which if we look at it from the expression here, we can understand that that is going to be obviously the parts where this sugar was on the surface there, correct?
pH
That
21 minus.
is going to be the lowering part here,
Correct. Yes.
right? So this lowering here is going to be something which should be proportional to mole fraction of what?
The water. I mean, either
Not
water
really mole fraction of solute over there.
solute. Yes.
Solute is my sugar over here,
Yeah. Oh, sorry. My bad. Yes. Correct. Correct. Correct.
right? It is not really mole fraction of solute. It depends on particles of solute.
Occupying
More
the
exactly.
upper surface. Yeah. Hmm.
So when you end up writing it mathematically here, what happens is you end up now defining a new term called delta P. This delta vapor pressure is usually not written as delta vapor pressure, it is written as delta P.
Hmm.
So we now define a new term called relative lowering of vapor pressure.
Hmm.
This is a new mathematical function. If you end up writing this, this will come out to be equal to your mole fraction of solute. Literal.
Okay. Yeah.
Solute
Yes.
non-volatile. So this is a property which is what to say, a function which depends on number of solute particles in
Hmm.
solution.
Yeah.
Fair so far?
Yes, sir. Yeah.
So this property, this type of mathematical function now gets a new name called as a colligative property.
Yes, sir. Yeah.
So what is this colligative property? A colligative property is a mathematical function defined for a solution. All right. So it's a mathematical property which gets defined for a solution, a mathematical function defined for a solution, which is going to be depending on or depends only on number of particles of solute in solution. This is going to be obviously now that I'm defining a new term for it, that means quite a few of the properties of solutions are going to be this type of.
Yes, sir. Yeah. Sir, just 1 second. Can I just come back? Just one.
You have a question or you having something to do?
Just a second, sir. I'll be right back.
Good.
1 second.
Okay. So basically, colligative properties are going to be very important when it comes to solutions, mainly because when it comes to solutions, a large number of the properties of solutions are going to be behaving as colligative properties, where the properties are going to be mainly dependent on the number of solute particles present in the solution. So that is basically the idea over here. Let's continue on now. So the first colligative property is relative lowering of vapor pressure. Now the rest of the chapter is going to be more or less understanding the different properties associated with solution fluids. That's basically going to be a thing. You'll be learning about the next type of solution, which is going to be what to say, liquid plus liquid solution after this. And you'll learn the properties for liquid plus liquid solutions. And basically that's going to be the game. So you're going to be learning what happens when you're going to be having liquid plus solid solutions and liquid plus liquid solutions and the various properties of it. So more or less, this is going to be the entire chapter there. It is not going to be that complicated.
Mhm.
As I said, some of the properties will be related to mole fraction, some of those colligative properties, and some of those colligative properties will also be related to molality. Why? Because both of them are mathematical functions which are not going to be dependent on temperature, and they are not going to be changing with temperature. So because they are a constant over temperature, you can use them and proceed on with understanding.
Hmm.
Now, This basically is sufficient enough of an overview here because we don't have time. I do remember promising that I'll shut up by around 9:15 to 9:30. How is your situation overall otherwise?
It's regarding what, like exactly?
School.
School. It's it's fine. Yeah. I
No,
mean,
I'm asking from the point of view of the say shuffling. You should have gotten a shuffling results by now.
yeah, I got the first batch.
Same batch still.
So
So
okay.
survive.
Yeah. So they considered the entire year. That's why.
That's why you survived.
Yeah.
Seriously.
I mean, I think even if it wasn't for that, I would have survived. But like, not many, not everyone else performed similar to me or like less.
What was your final score?
So they didn't give results. So they just gave batches.
What the seriously?
Yes, so they don't. They're weird, very weird. I'll go ask like the teacher. I
Huh?
wanted to know my. I was gonna go ask my teacher anyways for my performance in the reshuffling test. I'll
Huh?
yeah. If I get the, once I get there, I'll tell you. So yeah,
Oh, you're gonna go ask anyway individually. Okay, huh?
yeah.
Cool, 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 cool.
If they
But
let me know,
this
I'll
is
tell you.
weird. Seriously, they didn't give you results, is it?
Yes, so generally they don't give the results for a reshuffling test.
Because they can dodge then.
Yeah, exactly. They are, they considered board results as well this time. I don't know why. Yeah.
Anything and everything to basically make it more vague.
Yeah. Yeah.
So they still do the nonsense they used to do earlier then. So
Yes,
there are some paying customers in the first batch then.
yes, sir. Oh, no, no, no. I don't think so. I mean,
Possibly
mainly our batch is still in our class. Only if like four people from other batches came.
only four people from. Okay, maybe second batch then maybe there will be paying customers then.
My one of my friends got like the third batch, and he talked to a teacher and got second batch.
Same teachers are teaching, I suppose, nah?
Same teachers for us. Yeah. For like the second batch, our math teacher is going to teach them.
Hmm?
Our math teacher is going to teach second batch, like for a change.
So basically same teacher, nah?
Yeah.
And chemistry teacher is also same
Yes,
in
sir.
all first, second, and third.
Yes.
So all first three batches are same people only.
No, sir. Second batch and third batch. Sorry, only second batch. Our math teacher changed. Like our math teacher went to teach their batch.
Okay, he's not going, he's not been teaching them till now. He's
No,
going to teach.
he used to only teach our batch. Now he's teaching two batches plus first year batch.
Okay, first year batch, juniors, okay, huh, fair.
Yeah.
Okay, so organic, how are things? They're going to be going full on.
Yes, sir. Yeah.
What are your thoughts on that? Have you started revising? Have you started going through full, what to say, entire history of organic which you have covered so far?
Yes, sir. I went through the notes. Yeah. It was fairly okay.
Have you gone through it again now?
Again.
You
Uh,
should.
okay. Yeah, I
Should
was
be
gonna do
starting
it
tomorrow,
tomorrow.
right? It's full.
Yeah, tomorrow morning I'll do it.
June 4th is a holiday?
June. You don't.
Yeah, it
No,
should be a
sir.
holiday. Election results day is holiday for sure. Huh?
Second day. Okay.
Huh. Is it election results day? No, it is definitely a holiday.
Yeah, maybe. Yeah. Sir,
Then mostly I will catch up with you on that day, Tuesday.
sir, is it true that somebody got 360 in advance this year?
360 in advance this year.
Yeah,
Honestly, I haven't heard about where from where exactly.
Alan.
Alan.
Yeah,
Possibilities there.
okay.
But I'm not 100% sure. Because this time, from what I heard, the max paper was doable, nothing too exceptional. Chemistry was a tough one. So if the kids could have done chemistry well, they would have survived off. Possibilities there.
Sir, also like for solutions, like how like common is it in mains and advance?
Repeat. This
Solutions.
chapter,
Yes, sir. Yeah.
this chapter appears relatively only. What to say? There will be a question.
Main.
Mains, definitely there will be one question. And advanced, yeah, usually there will be a question. Sometimes they'll combine it with another chapter and what does they make the question, which will make it even more trickier. For instance, in advanced, they like to combine it with thermodynamics. They like to combine solutions with ionic equilibrium, and sometimes they can combine solutions with ionic equilibrium and chemical kinetics together. So when you end up combining it with another chapter, it becomes more potentially deadlier as a question.
Yes.
So it's a very easy topic to be combined with many topics.
Okay.
You think almost all the reactions you learn are in solution form.
Yeah, that's true. Yeah.
So obviously it has enormous potential for combination.
Yeah. Yes.
Um, that's basically it. What else? Yeah, we will close the session here. Any questions you have to ask before we disperse? You're going to be going into a very grueling round now. There will be no breaks.
Yeah. Yes.
Your vacation is over.
Mm.
Whatever freedom you had is done. No more breaks till the game's officially, at least partially flagged off.
Yes. Yes.
So, what are your thoughts? What are any questions you got?
Nothing. So nothing. Yeah.
All right. Bye bye. Have a good night. I will see you on Tuesday
Yes, sir. Yeah.
or Wednesday mostly.
Yes.
Wednesday anytime. Tuesday also mostly.
Okay, sir.
Bye bye.
Thank you, sir. Good night, sir.
Have a good day tomorrow.
Thank you, sir. Yeah. You too. Yeah.